Hello. Now we will solve an example where this capacitor is there and this capacitor is partially filled by a dielectric. So this dielectric is having same cross-section area as the cross-section area of the capacitor, but its width is not similar to the width of the capacitor. So the width of the dielectric is D0 and the width of the capacitor is given D. Cross-section area is same. Okay, this dielectric constant of this dielectric is given K, and outside of that is air, so dielectric constant for air is 1. Okay, so we want to calculate the effective capacitance of this system. Okay, so to calculate effective capacitance of this system, since cross-section area is same, one thing we know about the capacitors, at any point of time we can introduce a conductor inside the capacitor of 0 thickness. And if we introduce a conductor of 0 thickness inside the capacitance will not change. The system will remain same. So here, what I'm going to do here, I'll introduce one conductor here of 0 thickness, same cross-section area, and one conductor here of 0 thickness and same cross-section area. Okay. So now if we see, there is one conductor, second conductor, third conductor, and fourth conductor. There are total 4 conductors. 4. So this is my C1. Basically, this is one capacitor. This is my C2. This is another capacitor. And this is my C3. That is another capacitor. So I divided a single capacitor into 3 capacitors. And if I treat this single capacitor as 3 capacitors, the value of capacitance, all the properties of the capacitance, they will remain same. Okay. So this whole system can be replaced by series combination of 3 capacitors having the same cross-section area. Every capacitor is having the same cross-section area, A, and their width is little bit different. So here the width is x1. So here the width will become D minus D0 minus of x1. Okay, so this width is x1, this is D0, and this one is D minus D0 minus of x1. And this capacitor is completely filled by the dielectric of dielectric constant K. So capacitance of this capacitor is C1. I'm defining this as C2. I'm defining this as C3. And we have ready-made formulas to calculate the capacitance if the capacitor is completely filled by the dielectric. So for C1, we can use the formula. The capacitance formula is A epsilon upon D. That's a general formula for capacitance, where this epsilon is permittivity of material inside the capacitor. When it is air, we'll write epsilon naught, and when it is a dielectric, we'll write epsilon naught times of K. Okay, so if I use this formula and if I calculate the value of C1, that will be equals to A epsilon naught, because there is an air inside of C1, divided by x1. This is the capacitance of first capacitor. C2, second capacitor, is completely filled by the dielectric. So it will be A epsilon naught K, because this is the permittivity of this medium, divided by D0. This is the second one. And C3 will be equals to A epsilon naught upon D minus D0 minus of x1, because third capacitor inside is air only. And these 3 capacitors, they are connected in series. So for series combination, the formula is 1 upon C effective is 1 upon C1 plus 1 upon C2 plus 1 upon C3. That's the formula to calculate the net capacitance of 3 capacitors connected in series. Okay, we can take these. So C1, so 1 upon C1 will become x1 upon A epsilon naught, plus 1 upon C2 will become D0 upon A epsilon naught times of K, and 1 upon C3 will become D minus D0 minus x1 divided by A epsilon naught. So in this case, let's take 1 upon A epsilon naught K common. If I take 1 upon A epsilon naught times of K common, there is no K here. So Upside it will be x1 times of k plus d naught, because there was a k here, and plus d times of k minus d naught times of k minus x1 times of k. So 1 upon C effective will become 1 upon A epsilon naught k. Now you see x1 times of k here as well as x1 times of k. One is in positive and one is negative. So that will become d naught plus, we can take k common from there, it will be d minus d naught times of k. So C effective will be A epsilon naught k divided by d plus d minus d naught times of k. That becomes the effective capacitance of this whole system. Okay. Now, one more thing we can see here actually, if I rewrite this formula, 1 upon C effective is equals to 1 upon A epsilon naught k. This formula, if you see, if A epsilon naught k, if I divide the whole formula, then it will be d naught upon A epsilon naught k plus d minus d naught upon A epsilon naught. Okay, this formula, I just divided that after simplifying it. And let's see that structure one more time. This is structure one more time, but this time what I'm going to do, there was this capacitor and the dielectric was placed somewhere in between the capacitor. And this time what I'm going to do, this dielectric, I'm going to shift the dielectric at one of the corner. So if I shift the dielectric at one of the corner, like here, without changing anything, so this will be d naught and the remaining distance will become d minus d naught. Because total width is d and width of this was d naught. If I shift it on one end, the remaining side, which is the air, remaining side will become d minus d naught. I'm just doing that. And if I use the same principle one more time, meaning by introducing the conductor, but this time I'm introducing one conductor, not the two. So this system, if you see, this system will resemble two capacitors, where this is K and this is D naught, and this capacitor is having width D minus D naught. You see, this is one capacitor. I've introduced one metallic plate here. So this becomes one capacitor which is completely filled by the dielectric, and this becomes another capacitor which is filled by the air. And they are in series. Same principle I have applied. Only thing I did differently here, I shifted the dielectric. Okay. So in this case, if this is the C1 dash, I am calling this as C1 dash and this as C2 dash. So the value of C1 dash, if you see,